Hey everyone, welcome back. So today we're going to be talking about the ROC curve, which officially stands for the receiver operating characteristic. Now the reason I didn't write that whole phrase on the board is because it's not very helpful. Just a quick history lesson, it was called that because it was initially used by the US Army to see whether or not they were doing a good job of predicting enemy aircraft. So we're going to do a little bit of an example that's more relatable today. So let's say that you are running a business called Statflix. So Statflix hosts movies about statistics for people to watch, and you have a bunch of different users. Now, in any such subscription service, one big problem is called churn. So churn happens when you are at risk of an existing customer leaving. So they might be leaving for various reasons. Maybe they don't use your service enough. Maybe it's too expensive for them. But either way, churn is something that businesses try to predict really well. And the reason is because when you think about keeping an existing customer versus signing on a new customer, it's much cheaper to keep the existing customer. So if that existing customer is going to leave, we can try to give them some free things. We can be like, oh, here's a free month. Here's $5 off of your plan or something. And we can try to get them to stay because that's going to be easier for us than losing them and trying to sign on someone completely different. So today we're going to be using that as our example. We're going to be trying to predict churn. And the whole goal of this video is not the model itself. We'll see that that gets explained pretty quickly. The whole goal of this video is judging whether the model and the predictions that we get from the model are good or bad. And we'll see how the ROC curve factors in just a moment. But first, let's go through the beginning, the machine learning framework. So let's say you have a big data set of customers and you split them up into a training and testing set. You use the training set to build the model, as always. And we won't worry about the model, just it could be anything. Let's just say it's a logistic regression to be simple. And that gets called M. Now you use your model M, which was built on the training set. And you feed in your testing set, which your model has never seen before. And you output some probabilities for every single customer in the testing set for how likely we predict that customer is to churn. So we get some probability between 0, which means the customer is very likely not to churn, versus 100%, which means the customer is very, very likely to churn. Now, we're actually not done, because if we actually want to make some kind of decision, we want to decide which customers to send free things to and which to not send free things to, we as the data scientists need to do one last thing. We need to draw a line somewhere between the 0 and 100 called a cutoff or a threshold, which says that everyone to the left of that line does not get any freebies, and everyone to the right of that line does. For example, just to keep things simple, let's say I drew the line there around 50%. That would mean that if my model has a less than 50% chance of you churning, I'm not going to send any free things to you. I'm just going to assume you won't churn. But if my model has a greater than 50% chance that you're going to churn, I will try and keep you as a customer by offering you things, okay? And that threshold is really up to us. As we'll see, when we change that threshold, interesting things happen. Now, before we get to that, let's look at an old friend called the confusion matrix. Now, I have a video on the confusion matrix, which I'll post below, but it's pretty easy to understand. It's just a simple 2x2 matrix where the rows are whether the customer will actually churn or not actually churn. So churn versus not churn. And the columns are whether we predict that customer to churn or predict them not to churn. So C and NC for the columns. And just to relate this back to what I drew above, everyone in the C, so everyone in the predicted churn, would be everybody who is to the right of this black line, and everyone in the predicted not churn would be everyone to the left of that black line. Now, each of these components has a special name. So the two that we would like to maximize are called true positives. This means that these are people who would churn, and we predicted they would churn. This is probably best case scenario, so we can try and keep these people as customers. The next best one is true negative, which means that these people will not churn, and we predicted they will not churn, so we don't unnecessarily send them free things because they wouldn't have churned anyway. Now, the most disastrous one is called false negative. These are people who would actually churn, but we did not catch them, so we did not send them any free things, and we probably would lose them as customers. And another bad one is called false positive. So these are people who would actually not churn, but we thought they would, so we sent them resources unnecessarily, okay? So these are the 4 components of the confusion matrix. Now we're going to start talking about how the ROC curve starts gaining its form. The ROC curve says, okay, I'm going to take these 4 components and I'm going to derive 2 metrics from there. 2 metrics that tell a very interesting story. The first of those metrics is called the TPR, or true positive rate. And the calculation is pretty simple. The calculation is just TP over TP plus FN. So let's look at the table again to get an idea of what that actually means in real world terms. So that's basically only looking at the top row. So notice this calculation only takes into account things in the top row. So this calculation is answering the question of all the people that will churn, that's the top row, what percentage do I catch? This is also sometimes called the recall. So obviously this is something I want to maximize, right? Because I'm saying that of all the customers that will churn, I want the percentage that I catch and that I can send resources to be very high. So I want to maximize my true positive rate. Now, the other metric is based on the bottom row, and that is based on all the customers that would not actually churn. And this is called the false positive rate. A very similar calculation. And the story here is that we divide FP by the sum of the two cells in the bottom row. Now, this answers the question of all the customers that will not churn, how many do I predict incorrectly? That's why the FP is the numerator here. And clearly I would like to minimize this because I want that error rate to be small. So the ROC curve begins its story by saying I have this TPR and FPR, and I would like to maximize my TPR and minimize my FPR. Now we can also plot these. Since these are only two metrics, it's pretty easy for us to plot in a simple two-dimensional space. So here is that plot. Both of these metrics clearly are running between 0 and 1. They're bounded between 0 and 1. So we can put FPR on the x-axis and TPR on the y-axis. Now, a couple of things I'll note is that what's the best case scenario? The absolute best case scenario would be if TPR was 1, so we catch everybody who's going to churn, and FPR was 0. So our error rate on people who will not churn is 0. And that graphically is at this star up here. So we would love for our model to output predictions that lead to us being near this top left corner. Now, the last thing I'll state on here is that where do we not want to be? We don't want to be anywhere below this diagonal line. So although I won't prove it, if we go anywhere below this diagonal line, then we are basically predicting worse than random guessing. And we could essentially do better than random guessing by taking all of those predictions, inverting them, and then suddenly we're above this diagonal line. So there's really no excuse for any model we built to be below the diagonal line. So the two things you want to take away from this plot are that never be below the diagonal line and try to be as close to this upper left corner as possible. Now let's continue the story. Let's see what happens when we take this threshold and we move it around. What if we move it really close to 0? What if we move it really close to 100? And we'll talk about the reasons that you would do that in a real business. So A would be, let's say we set a very low threshold. So again, the story is that our model outputted some probabilities of churning for each customer, and we're going to set that threshold very low, so around here, near 0. Why would we do that? We would do that, for example, if we really, really want to catch people who are going to churn, and we have basically a lot of resources. The reason is that this means that we're going to predict basically all of the customers are going to churn. Virtually all the customers are going to churn based on setting the threshold really low. So we're going to send them all free things. Now, if you don't have a ton of resources to give, this is a waste of money. But if you have infinite resources for some reason, then this might be the course of action you take. So again, what this means is that everyone to the left is predicted not to churn, which is very few people. And everyone to the right is predicted to churn, which is most of the people in our test set. What does that mean for our true positive rate and our false positive rate? Well, the true positive rate is going to be really, really high, almost close to 1. And the reason is that the true positive rate, again, measures of all the people that will churn, what percentage do I catch? And since I'm predicting basically everybody will churn, I'm going to catch most of them just by virtue of predicting everybody will churn. So that's why my true positive rate is high. Now, this sounds good so far, but we start getting an idea of the trade-off between these two metrics now when we look at what happens to your false positive rate. Again, the false positive rate is of all the people that will not churn, what percentage am I wrong about? And by predicting that barely any people will not churn, I'm missing out on predicting correctly a lot of people that would not actually churn. If that's a little bit confusing, let me show a little graphically. So we're looking at this plot again, and let's say that the people who will not actually churn are around here, right? That would make a little bit more sense. We set our threshold really low, but the threshold in reality is probably a little bit higher. So what we're doing is for this group of people who would not actually churn, what percentage are we wrong about? Well, the percentage that we're correct about is just this little piece to the left of this dashed line. So we're wrong about most of them. What that means is that our false positive rate is going to be very high. So the story here is that by setting our threshold super low, we do get great performance on our true positive rate, but we are getting that because we are sacrificing our false positive rate. So if I were to plot this case, it would be high FPR and high TPR. So case A would be around here. And notice this is not very close to this gold standard. So let's say that, okay, what if I try it the other way around? What if I set my threshold very, very high? So I set it close to 100%. And so everyone to the left of that threshold, I say will not churn. And everyone to the right of that threshold, I say will churn. Now you can basically just take all the words I said and invert them. But in a nutshell, what's happening now is that our true positive rate is very low. Why? Because our true positive rate, again, measures what percentage of people who will actually churn do I capture. And now I'm predicting that barely any people will actually churn, just the people that I'm super confident about. So I'm going to do a pretty bad job in terms of true positive rate. It's going to be very low. But that also means that my false positive rate is now much better. The reason is because now I'm predicting that most people in my test set will not churn. Therefore, when it comes time to ask the question about what percentage of those people am I wrong about, it's virtually nobody. Because again, if these are the people who actually will not churn, then I'm comfortably capturing all of them. And I see that I have TPR low and FPR low. And really quick before I plot this, why would you want to do this in a business setting? This would be if you don't have a lot of resources, like you don't want to give out too many freebies and free things to customers, and you can only afford to give these free things to customers who are very, very likely to churn. Okay, so different business scenarios here. So this case B would be both of these metrics are low, and we would be over here. So notice this is also not close to the gold standard. So now let's think about all the stories in between. We looked at the two extremes, but in reality, you're going to set your threshold probably somewhere more comfortably in between. So let's say that we're at point B. So we're at somewhere where the FPR is low and the TPR is low. And we're like, this is not a good situation to be in. I would like to increase my TPR by a little bit. Now looking at scenario B, I could increase my true positive rate a little bit by shifting my threshold back. So instead of being way up here, I could scale it back a little bit. So imagine my threshold was now at this blue line over here. I'm going to improve my true positive rate. Why? Because now I'm catching more people that will actually churn by virtue of shifting my threshold back. So my TPR is going to go up. Let's think about what's going to happen to my FPR. My FPR honestly won't change by that much, if at all. And the reason is that false positive rate, again, measures of the people that will not churn, how many am I wrong about? And of course, these are the people that will not churn. So by shifting my threshold back a little bit, that actually doesn't change my false positive rate at all for this specific example. And in general, it's not going to change it by much. The intuitive reason for that is because the people that will not churn are probably near the lower end of this bar. So if your threshold is already way over there, by taking a little bit in this direction, you're not going to be sacrificing this FPR metric too much. So the story we get graphically is that we increase our TPR by a good amount and only sacrifice our FPR by a little bit. So we move from B to maybe over here. And if we continue the story, the ROC curve ends up looking a little bit like this. So it's kind of like starts going very fast, kind of plateaus off and goes like this. And the reason that it's a curve and not a line is because of the story I was telling here. The reason it's a curve is that if I'm at either extreme, so either at point A or point B, that means that one of my metrics is suffering a lot. If I'm at point A, then the metric that's suffering a lot is the false positive rate. If I'm at point B, the metric that's suffering a lot is my true positive rate. Now, if I want to improve that respective metric by just a little bit, I would shift my threshold in either direction and I would improve that metric drastically. And I wouldn't suffer too much on the other metric, okay? So that's the whole point of this being a curve, is that I get great gains in one direction and only give up little things in the other direction if I'm at either extreme. Now that story becomes less true as I move towards the middle of the curve. Now it's more of a one-to-one trade-off, okay? So that's why this is called a ROC curve. So I want to be really clear because we've said a lot of words, but I want to tie everything together into one nice narrative. What is the ROC curve? The ROC curve assumes that you have some probabilities that are given back by your model. Again, the model doesn't matter, but you have some probabilities given back by your model. Now you as the data scientist realize that I need to set some kind of threshold. And above that threshold, I'm going to take one action, and below that threshold, I'll take some other action. Now, this threshold might be dependent on your business scenario, depending on how many resources you have and how desperate you are to catch customers who are going to churn. So that threshold is up to you, but you also want to understand how changing that threshold relates to this really cool trade-off between true positive rate and false positive rate. And that's exactly what the ROC curve graphs. So you can basically construct a ROC curve by taking a bunch of different thresholds from 0 to 100. So let's say you check the threshold at 0%, 1%, 2%, and you check all these different thresholds. And for each threshold, you construct a different confusion matrix. You'll get different values for TPR and FPR. You plot those values on your graph. And when you connect all those dots together, you're going to get your ROC curve. And how do we know if one ROC curve is quote unquote better than the other? A metric that people often use, and the last thing we'll talk about in this video, is called AUC, or area under curve. Now, the disclaimer I'll say is that AUC is a single number that's constructed from an entire ROC curve, which means that you cannot capture all the dynamics in that ROC curve. And the idea for this is purely mathematical. The ROC curve is a two-dimensional creature, and you are reducing it to a one-dimensional metric, so you're going to be losing a little bit of information. But people do use this as a proxy for whether one ROC curve is better than a different ROC curve. So what I've drawn down here are 3 different sample ROC curves, and the dashed line again is the y equals x line. Now, which of these ROC curves would you prefer? I think even without thinking about it too much, you would probably prefer the one on the very right. And the very easy graphical explanation for that is because there is a point on that curve which is very close to our gold standard. Remember, our gold standard is at the upper left-hand corner. If we look at these other curves, this one is almost a flat line. This one is a little bit better, but this one has a point, a threshold that I can pick, where if I were to pick that threshold, I would get very close to my gold standard of true positive rate being 1, false positive rate being 0. But just to dive a little bit deeper for the end of this video in why you would choose this one, it's really about the trade-off you're making between FPR and TPR. For example, if we look at this curve here, this blue line is almost the same thing as the diagonal black line we're looking at, which means that if I want a little bit of improvement in my TPR, I have to basically sacrifice the same amount in my FPR, which is not a great situation to be in. Contrast that with the one over here, which we already said was best, and you see that I get a lot of improvement in my TPR, so I can move up a lot on the y-axis, and I don't have to move that much on the x-axis. So the trade-offs are a lot better here. I can get a lot of return on one of my metrics by sacrificing almost nothing on my other metric, and that is a situation I would like to be in. And so we know this one is better by basically just considering the area that's under that curve. So you can see that the area under this blue curve is highest for the one on the right, and it's the lowest for the one on the left. So that's why people use this area under curve metric as kind of a proxy for determining which is the best ROC curve. But again, it can't capture all of the little dynamics because all it's doing is just getting the area. So that was in a nutshell the ROC curve. Hopefully it helped you understand how we judge models in machine learning even better. If you have any questions at all, please leave them in the comments below. Please like and subscribe for more videos just like this, and I'll see you next time.